Ever wonder how your smartwatch detects stress, or how doctors spot heart issues from a messy ECG? It's all about decoding the hidden language of our bodies, those electrical signals that pulse through our hearts, brains, and muscles. But here's the catch. These signals are like a chaotic symphony. Noisy, ever-changing, and hard to untangle. Today, we're exploring a breakthrough called PhysioWave that's turning this chaos into clarity. Let's dive in. First, let's talk about the problem. Imagine trying to hear a conversation in a crowded room. That's what analyzing physiological signals is like. Heartbeats, brainwaves, and muscle activity are full of noise. Think motion artifacts, random interference, and signals that shift faster than a chameleon. Traditional methods, like basic filters or looking at data over time, just can't keep up. They either miss the big picture or get lost in the static. But here's where PhysioWave shines. It's like giving your data a superpower, the ability to see at multiple scales. How? It uses wavelet transforms. Think of them as a zoom lens for signals. Unlike regular filters that treat everything the same, wavelets can focus on quick bursts, like a heartbeat spike, and slower trends, like a gradual brainwave shift. It's like having a microscope and a telescope in one tool. But wait, there's more. PhysioWave teams up with a transformer model, which acts like a supercharged AI that understands context. Together, they don't just see the noise, they learn to ignore it. Here's the genius part. They use frequency-guided masking. Imagine training a model by hiding the most important parts of a signal and forcing it to guess the rest. By focusing on high-energy sections, like a sharp ECG peak, the model becomes a detective picking out what really matters. Now here's where it gets truly impressive. PhysioWave isn't just for one type of signal. It's a multi-modal marvel, handling ECGs, EMGs, and even EEGs all at once. How? It uses specialized backbones for each signal type and dynamically weights their contributions. It's like having a team of experts, each skilled in their own field, collaborating to solve a complex puzzle. This adaptability could make wearable tech smarter, more accurate, and way more reliable. The results? Mind-blowing. In tests, PhysioWave achieved 94.5% accuracy in classifying muscle movements and 66.7% in detecting heart irregularities, setting new records. And because it's trained on massive datasets, like 823 GB of EMG data, it adapts to differences in people, environments, and even individual quirks. No more one-size-fits-all solutions. So what's next? This isn't just a tech win, it's a paradigm shift. But here's another question. How do models like OpenECG and ECG-Chat learn to interpret these signals in the first place? Let's break it down. Training AI to read your heartbeats or understand muscle movements starts with one thing: data. But not just any data. Clean, consistent, and ready to teach machines how to interpret signals from the human body. Take ECG data, for example. These recordings capture the heart's electrical activity, but raw data is messy. To make sense of it, we standardize everything, adjusting every recording to the same sampling rate, like syncing a playlist to the same tempo. Then we organize it into a special format called HDF5, a digital filing cabinet where each heartbeat is neatly categorized by patient, lead, and time window. This structure lets models quickly access and learn from millions of heartbeats. But where does this data come from? Datasets like MIMIC-IV ECG hold 800,000 heart recordings from 160,000 patients, while MEDALCare XL simulates real-world ECGs with noise and filters. These aren't just numbers, they're tools to train AI to spot patterns doctors might miss. Now here's where things get really interesting. Models like OpenECG use self-supervised learning to teach themselves by analyzing millions of ECGs. Techniques like SimCLR, think of it as a puzzle where the model learns to recognize patterns, and MAE, like filling in missing pieces of a picture, help the AI identify consistent features across diverse datasets. But OpenECG is just the start. Enter ECG-Chat, which takes it further by combining heart data with medical text. Imagine a system that can generate accurate diagnostic reports, like a doctor's notes, by understanding both the electrical signals and medical terminology. And here's the kicker. It uses external medical knowledge to avoid hallucinations, ensuring it doesn't invent symptoms that aren't there. It's like having an AI intern who double-checks its work with a medical textbook. So what's the big takeaway? Self-supervised learning is unlocking new possibilities by leveraging unlabeled data, which is everywhere. Whether it's decoding brain signals, diagnosing heart conditions, or predicting anomalies, these models are bridging the gap between raw data and actionable insights. The future of healthcare isn't just smarter, it's predictive, personalized, and powered by AI. Thanks for watching. If you want to dive deeper into the science behind these breakthroughs, hit subscribe and explore the links below. Until next time, stay curious, stay informed, and keep exploring the invisible world inside you.